Hi, everybody. There's a ambiguous title, weird and familiar, right? Because this is the last talk, we're going to get a little contextual, maybe a little metaphysical, and also a little bit sentimental, right? But we're going to try to not introduce any new concepts, but to understand both that the concepts that we've learned and that we're talking about, if universality is universal, then we should see the same kind of behaviors that we've been talking about out there in the universe. Sadly, at least for now, we can only explore an infinitesimally small portion of our universe. But one thing I say that I think is kind of cute is that, if you want to test for universality, leaving Earth and going and exploring the universe and seeking similar things is one way to do it, right? Maybe you would say that's the geologist's way to do it, right? A physicist expects universality if their theory is beautiful. If you're an observationalist, you have to go out and look, okay? So there's this part that when we go to other worlds, these worlds are very strange and they're also familiar. And so that's where the weird and familiar comes from. The other part is that we're going to talk a little bit about a phenomenon known as global weirding, which is all of the erratic, extreme behavior that surrounds climate change, right? And hopefully that'll start to make some sense. So I've drawn out here the, the planets, right? So this is us in Doug's drawing. We don't much care about this little sun-baked rock right here, right? You can ignore that for now. Venus is a baking hellhole that yet surprisingly has some similar things to Earth we're going to get into. We've been focused on planet Earth so far. I'm not going to go through all these planets, but as we go through some different phenomena, I want to point out there's surprising occurrence maybe in different planets, in very different environments, in very different materials, and things that are actually the same, right? So maybe the first surprise is, you've seen me now a bunch of times draw a little mountain range, and you've probably seen me draw this mountain range last time where we had drainage networks on it, right? So we have erosional channels that make these dendritic patterns. They're actually fractal, but I don't feel like drawing enough scales to make them fractal, right? But we have this pattern, right? So on mountains with steep slopes, where it rains from above, we know that the water collects and it moves down. It follows paths of steepest descent on sloping surfaces, which end up being directed random walks. And those directed random walks run into each other and form convergent channel networks. So I argued to you before, right, that this is you're shocked, right? I argued with you before that this is a very generic phenomenon, right? That this is something that we could call directed percolation. So the arguments that I made to you about the formation of erosional channel networks were very generic, right? Very generic. I just told you that water wants to go downhill, that it's got bumps in the way, that it finds a path of steepest ascent, which is a directed random walk, and then if it's able to pick up particles, that erodes and makes channels, right? So maybe this isn't surprising, but this pattern, which is about the most universal, repeated, geomorphic pattern that we see on the surface of Earth, also appears other places. Can anyone tell me where else they appear? Where else do we see erosional dendritic channel networks like this? What? Mars. Check. Titan. A little moon of Jupiter. Check. Okay? At least these two places. Now, it's worth considering, if you go to Mars, these channel networks were probably pretty similar to Earth. What I mean by that is that they're eroding into basalt, volcanic rock mostly, which is also a common rock that we have on Earth. There's no longer liquid water on the surface of Mars today, but we have a pretty good amount of evidence now that there was a lot of liquid water on Mars in the past, that Mars used to be warmer and wetter and subsequently lost its magnetic field. And when it lost its magnetic field, it lost its capacity to hold on to its atmosphere. And stripped of its atmosphere, Mars got cold and dead. and a planet that used to be coursing with liquid water 4 billion years ago and was pretty similar to Earth in the formation of water-formed erosional drainage networks cutting into volcanic rocks, now is sitting there and these networks are dormant. I should point out, though, that there's a big difference. There's a lot of differences in Mars. Remember I told you about plate tectonics, and almost all the first half of the chalk talks we drew planet Earth and we talked about plate tectonics. Mars doesn't have any plate tectonics. And so the channels that were formed 4 billion years ago are actually still just sitting there. On Earth, they would have been subducted, collided, melted, turned in, mixed with the mantle, and vomited up again as volcanoes or at spreading centers over and over and over. That does not happen on Mars. So these channels on Mars, they get pockmarked with craters. We talked about this a little bit before. And so we know that they're old because they've been plastered with craters on top of them since then. Nonetheless, 4 billion years ago, there were river channels on Earth, right? Or on Mars. Titan's pretty weird. Titan is more surprising, perhaps. I mean, Mars is surprising under present environmental conditions, but we have a lot of circumstantial evidence that we've been building since the 1970s that Mars used to be warm and wet. We didn't get a close look at Titan until 2004. Titan, this moon of Saturn, is enshrouded in this haze around it, and this haze that surrounds it means that from a telescope, all that we can see is the thick atmosphere, and we were unable to see what lies underneath, right? So in 2004, there was this miracle that happened, okay? So Cassini was a flyby mission, flying this way outward into the solar system, and Cassini flew close to Titan, and as Cassini flew close to Titan, it spat out a little probe, which I'll make look like a flying saucer, kind of. And this probe didn't know what it was going to see, okay? It didn't know if it was going to land on solid or liquid, right? We didn't know what was underneath the haze, and this probe, called the Huygens probe, went screaming through the haze, and when it got through the upper haze of the atmosphere and got a clear view below, from several kilometers above, it snapped a few pictures on its descent. And what do you think it saw on its descent? This. It saw erosional channel networks, but here's the thing. The mountains on Titan are made of water, which under those temperatures is hard as rock, right? And these channels drain into basins that are filled, they're seas, and the seas are liquid, but they're seas of ethane and methane, which under those temperature and pressure conditions are a liquid, not a solid, okay? So we have liquid methane and ethane apparently in a hydrologic cycle, or whatever word you use when it's methane and ethane instead of water, apparently raining down onto mountains made of water, breaking that water into pebbles, and the pebbles are being transported by ethane and methane down into ethane and methane seas. So, weird. We would never expect something like this. The viscosities and densities are all different. The strength of the rock is all different and familiar. If you think about it, the conditions that I laid out for the formation of an erosional drainage network are fantastically generic, right? I basically said, if we have flow that takes directed random walks and it can pick up particles along the way, it will make this pattern. And indeed, that's what it does. I need to point out one other thing, which is true on Mars and on Titan. We don't just have observations of these networks. We have observations literally at the ground level. In the case of Mars, it's because we have lots of rovers that have driven over the surface of the Earth. In the case of Titan, it's because our weird little probe basically landed right here at the mouth of the canyon. And you know what we see when we look on the ground at Mars? And do you know what we see when we landed at the mouth of this canyon on Titan? We see a riverbed with nice rounded pebbles, and those pebbles are even arranged in this imbricated pattern. Pebbles are a little bit elongated and they kind of look like a set of dominoes that has been knocked over. The pictures from Mars are striking. You look at the sediments in the riverbed on Mars, and in a false color image where you tune it so that it looks the same as the Mojave Desert or somewhere, you would have literally no idea that you were looking on another planet. The pebbles are banging together. Remember, we talked about that all the way back in lecture 1, that if you start out with initially angular pebbles and they bang into each other, that you round off these corners and that the pebbles evolve toward these ellipsoids. And we see these beautifully rounded ellipsoid pebbles on Mars. The pebbles on Mars downstream are rounded. The pebbles on Mars upstream in the source waters are angular. And why wouldn't it be that way, right? Why wouldn't we have rock getting fragmented, falling into Plato's cube, banging into each other and rounding as they get transported downstream? The gravity's different. Otherwise, though, there's nothing about this. The things like gravity, things like fluid density, they affect this process, but mostly in terms of the rates, not in terms of the geometry, right? This probe, Huygens, that went screaming through the atmosphere on Titan, it lands, slams into the ground at about 100 G, okay? It has 2 cameras. The main camera opens up, dies before it takes a picture. The side backup emergency cam, which is a fisheye cam at an angle, opens up on the side, takes exactly one picture that it beams up to the Cassini satellite before it dies. And what is that picture? It is a field of rounded pebbles that came from the canyon above. And you look at this field of rounded pebbles that are partially buried in sand, and it looks just like a beach in Maine, right? Like, here's some pebbles with some sand around. And so remember, these pebbles are made of H2O. They're on a beach which is dry that presumably is sometimes in the past, maybe in the future, lapped with waves from an ethane and methane sea, okay? And so I bring these points up because, if you're an experimentalist, you're always trying to falsify your claims, right? As soon as you discover someone discovers a beautiful theory, you do everything you can to try to prove that it's wrong. When it comes to interrogating nature about the questions of universality, when it comes to seeking a way to falsify our models or our beliefs that things are truly generic and universal, the strongest test that I can think of is to go to other planets where everything is exceptional compared to Earth, and to realize that these exceptions prove the rules over and over and over again, right? And this is what we see when we explore other planets. It's actually shocking how familiar every landscape seems to be when we observe it, right? We go all the way out to Pluto, which used to be a planet when I was a child, and no longer is. And you see crumpled mountains. Clearly, there's collisional events causing plastic deformation of the rock. The rock way out there is what we would call ices of various kinds, nitrogen, things like this. You also see what look like frozen lakes with polygonal ground. Things formed by fracture, things formed by convection, and they're made of materials that are exotic to us, but the temperature and pressure conditions make them dynamically equivalent to the more common materials that we think of on Earth, right? And so rocks on Earth are made of silicates typically, and rocks on Titan or Pluto are made of water or nitrogen, respectively, things like that, right? So that's one thing that I want to bring up, is the ubiquity of these rivers. Next thing that I want to bring up is sand dunes, right? So, I like sand dunes. We've talked about them a little bit. Picture a sand dune here. I'll remind you again that I'm drawing here like a bar can sand dune. These are typical sand dunes in sediment-starved environments where the wind tends to blow in one dominant direction, in this case left to right. If I draw a cross-section through here, I'll remind you all of the transport process associated with sand dunes, right? So the profile of the sand dune looks like this, and essentially what's happening is that the wind is blowing, the wind is applying a stress, but that stress, remember, is a stress that is just above the threshold of motion. For the particles that make up the sand dune, that's the requisite conditions. If the wind blows too strong, the sand grains get picked up and leave, and if the wind blows too weak, the sand grains don't move at all. And so sand dunes exist where these particles are under this process of saltation, they're rolling and bouncing along, right? And the sand dune itself advances by erosion on the upwind side and deposition on the downwind side. So there's not just one kind of sand dune, right? So if you have more sediment available, enough to link up a bunch of bar cans, you actually end up with these things that we call transverse dunes, right? So the wind is still blowing, but instead of now an isolated bar can, they're big, long ridges. They still move left to right in the dominant wind, but they can extend laterally very, very far. If instead of a unidirectional wind, you have multi-directional winds, you can make other sand dune patterns. So there are places in the world where there are bidirectional wind. The wind switches like this. And in those situations, you get what we call linear sand dunes, which actually grow in this direction, right? So the net direction of transport is still left to right, but if it's sort of equal or sub-equal directional switching, you get these linear dunes. They're still moved by this process of saltation, sediment transport. Why am I bringing this up? Who wants to give me the list of where we found wind-blown sand dunes formed by saltation of particles just slightly above the threshold of motion? Someone shout out a planet where we found this. Mars, all right? So sand dunes on Mars. Well, actually, I'm going to give them a yellow check, right? Let's give them a yellow check for sand dunes. Sand dunes on Mars, yes. Your favorite. Titan, yeah. Sand dunes on Titan. Anyone else? What about this hellhole over here? Got him. Venus got him. Yeah. Yeah. You didn't read Andrew Gunn's paper? If you ever see this, Andrew, this one's for you. Where else? Where else? I had to look some of these up, I admit. You're all upset Io's on there. Nobody was complaining about Triton. Is that a moon of Neptune? I think. I think Triton is a moon of Neptune. Triton's got him. Yeah. You know where else?
You have to run Triton separately. Looks like it's on Neptune. Yeah. There you go.
Pluto. As far as we can tell right now, sand dunes are even more ubiquitous than river networks. So on planet Earth, we have river networks everywhere because in most places we have enough precipitation to have liquid water. Liquid water is a lot more dense than air is, so it's a hell of a lot more efficient at moving sediment. So on planet Earth, we only get aeolian or wind-blown sand dunes in places that are sufficiently dry and sufficiently windy that water is negligible, and then wind can come to the fore. But actually, when we survey the solar system today, what we find is that most of these planets are windy places. Most of them have a limited, sometimes no longer existent hydrologic cycle, whatever the equivalent is for liquid on those planets. But most of them do have a substantial amount of wind, powerful wind, and you have rock that is somehow, by some process or another, getting ground down into particles. Now, the one thing I want to point out is we call them sand dunes. On Earth, sand is a classification, right, for grains that are like larger than 60 microns and smaller than 2 millimeters or something like that. That classification on Earth has some kind of physical meaning to it, these sand dunes are not necessarily all sand-sized on other planets, right? So on Earth, things get smaller than 60 microns and they get sticky and clumpy. On some planets with different atmospheres and different gravities, even what we would call sand-sized stuff is very sticky and clumpy. And on other planets, things that we would think of as very sticky, clumpy dust is not sticky and clumpy at all at a similar size on another planet, right? So there's a lot of details about the electrostatics and about the interparticle potentials and gravity and atmosphere and all that stuff. So sand dunes are not all made of the same size or material everywhere. In fact, they're made of very exotic materials. On Titan, the sand, as far as we can tell, is some kind of hydrocarbons, okay? Also, the atmospheres are not the same. So our atmosphere is dominated by nitrogen, right? That's also true on Titan, it turns out. But on Mars, it's carbon dioxide. Carbon dioxide has a different viscosity and density from our air. I should also point out that the gravity on Mars is a little lower, so that might make it easier to move stuff. But the atmosphere is about 100 times thinner, so that should make it harder to move stuff. And it turns out that if you want to move sand grains of basalt on Mars, you need what we would consider hurricane strength winds, right? The wind velocities on Mars that are required to move a piece of sand are 100 times what they are here on Earth. But the density is about 100 times less. Guess what? In terms of the dimensionless stress, it's the same dimensionless stress, right? If you compare the driving fluid stress compared to the weight of the particle, you come up with a similar threshold on Mars that you do on Earth, okay? So sand dunes are also common. And the thing about it is, if you think about the fact that sand dunes only exist in conditions that are close to threshold for the particles that make them, that means that when you see sand dunes on another planet, even if you have very little data, if you know something about the particles and their size and their mass, then you can say a fair bit about what the wind conditions are on that planet. You know that they must be large enough to saltate those particles, and they must be small enough that they don't pick them up and suspend them, right? So these are like flow indicators of a very useful kind, right? All right, another feature, I'm loath to erase that. I'll leave it up for now. Right? So this I've drawn is a cracked ice network. We talked about this way back in the beginning, right? Of course, any cracked network might look like this, but I mentioned way back in lecture 1 that on Earth, we observed that when we look at fracture networks, that ice is special, right? And the thing that makes ice special is that, you know, when a crack forms, you'd think that a new crack that is growing, right? We imagine a crack tip that is focusing the stress and growing, that when it runs into a previously existing crack, that it will stop. Because you can't transmit an elastic stress over an air gap, right? And so generally, when we have crack networks, when we have a new crack come and run into an old crack, it stops. With ice, that doesn't happen, remember, because ice heals. Pretty much everywhere where we see fractured ice networks that's close to its critical temperature, right? There's liquid water around somewhere, either from beneath to rush in and fill the hole, or from water vapor from above, or from the sun melting the surface. And so everywhere that we see cracked ice sheets, we also have new sources. We have melting and refreezing and healing of these cracks. So we know that cracks that form in ice and that heal have a special geometry. And on Earth, that geometry is the same pretty much everywhere. And so when we go and we look at cracked ice networks on other planetary bodies, the ice material isn't the same, but when it's a sheet of ice that appears to crack and reheal and crack and reheal, we see not just qualitatively the same fracture patterns, we actually see quantitatively that they're very, very similar. So where else do we see cracked ice networks besides Sophie? Sophie can't tell, sorry. For the camera, it's Sophie's thesis, that's why she can't tell. Enceladus, okay. Oh, I used the same color for ice as I did for, that's not good. Here, I'm gonna use Pink. All right. Enceladus? Europa, right? Okay. Anywhere else that we know of? The Schuylkill.
During the winter.
During the winter. Sure, I mean Earth, yes. Sorry, all these things are on Earth, right? So, you know. We talked about other kinds of cracks, right? So we talked about mud cracks, right? And in particular, you know, we said, oh, look, if I just form mud cracks from one drying, they make all these T-junctions. But when we shrink and expand, then we know that those T's get twisted into Y's, and that we end up with networks that are, you know that I have trouble drawing hexagons, that under repeated freezing and thawing, that we end up with crack networks that are more hexagonal. I'll just have them pre-populated with hexagons on the board, right? So the point is that we see mud cracks on Earth in places where we have like shrinking and swelling soil that dries and cracks. And we know that if it gets repeated cycles of wetting and drying and cracking and swelling, that we change geometry, that we get hexagonal kind of patterns. Anybody want to tell me where we found mud cracks, where else in the solar system, and where we've even found hexagonal mud cracks? What? Not on Pluto. There is polygonal ground, but we don't think it's mud cracks. Things where it's mud cracks where like it's actually made of like mud, like clay and sand and stuff. Mars, yeah, Mars, right? So on Mars, well, whatever. What am I give up, you know, my colors. We have mud cracks on Mars too. We have mud cracks in ancient lake beds that now have been dry for 3 or 4 billion years, but seem like in the past that they not only had water and precipitation of clay and mud, but that it even like cycled wet and dry, like a totally normal, mundane for us and absolutely profound for Mars temperate hydrologic regime, right? So it's the geometry of these networks that can tell us. And it's this weird exception that proves the rule, right? So we see these repeated patterns in the landscapes, and they're repeated in terms of material behaviors too, okay? So like just to bring this home, you know, we've paid a lot of attention to Mars. You know, humans have sent a lot of spacecraft to Mars, and it is pretty close to us. And a lot of people are interested in whether or not life could have arisen there independently. So just to make the point, though, is about how similar it is. So on Mars, most lakes are in craters. That's a difference from Earth, right? We have tectonics all the time, crumpling and making mountains and valleys and stuff. On Mars, you have volcanoes and you have craters. Those are the things that make topography, right? So maybe the unusual part is that most basins on Mars are craters. But when you look at those craters, so you see at the rim of the craters, there are dendritic channel networks, right? So the flow is coming this way, and the flow was collecting and eroding and making these dendritic valleys. And sure enough, when you see that the channels run into an unconfined area in the basin, you see that the channels become distributary, that they spread out. And so we even see them making river deltas, indicating that this lake is like a sea and the sediments are depositing and growing in here. When you zoom in on these channels in some more detail, you see that they're meandering channels with scroll bars indicating persistent erosion on the outside and deposition on the inside, right? Just like we see on Earth. And then, as I mentioned before, if you zoom in even more on them, you see nice imbricated, rounded pebbles, okay? So the river systems on Mars have literally every single element in them that we see on Earth, right? Erosional networks, to depositional distributary deltas, to meandering rivers, to rounded pebbles, okay? Just to bring it home about how similar this is, okay? So I think that's pretty cool. So having hopefully just convinced you a little bit that a lot of what we've discovered is universal, at least in our little corner of the universe, I want to talk about another element of the weird. And I mentioned that before. This element that I want to talk about is what is these days commonly called global weirding. And if you're not familiar with the term, to me, I just mean that 1.5 C warming, 2 C warming is bad, right? I'll feel warmer in a 2 degree C warmer world. But our big concern is not, as you probably know, the mean temperature. It's the change in the extremes around the mean, right? It's that droughts get longer, that intense rainfall gets more intense, right? That the wet periods and the dry periods get extended in duration and intensity, right? And that triggers a whole bunch of other instabilities in the Earth system that we call global weirding. And a common term that people worry about in like climate systems and Earth system science is tipping points, right? Tipping points is not a term that was invented by the Earth system science community, but it seems like when you read popular science, or if I talk to any people who are not scientists, if they've ever heard of tipping points, it's in the context of climate change and like driving Earth system into some new state, right? So, the premise of the tipping point is something like this, right? So imagine that you have like a seesaw, which is balanced on one side right now. So we'll call this state 1. And this is like the Earth state that we're familiar with, right? So this might be like the state where, the ocean's thermohaline circulation that moves water and salt and temperature around is where it is. This might be the state where, the Sahel in Africa is in its current state, that it's semi-arid with rangeland and agriculture that it can still support, right? In other words, state 1 will just say whatever state our Earth system is in right now that we're familiar with, right? And the premise with the tipping point is that, you're applying some pressure, and applying some pressure could cause some change, but the system is pretty settled in its state. And so you apply a little bit of pressure, right? And the little bit of pressure that you're applying for a while is not sufficient to overcome the gravity of state 1, right? So state 1, it's trapped in this state, and you start to apply some pressure like rising temperature, and it doesn't do much, and it doesn't do much. And then at some point, you apply sufficient pressure that you tip the scale, right? And the system abruptly flips to a new state, right? So you can think of it, people think about it this way, it's a tipping point, but you could also think of it as like a capacitor that, you're storing, and then you discharge catastrophically, right? But the point is, here, it's that you can accumulate a bunch of stress without much change, and then suddenly change and flip from one state that is stable to a new state. The new state to us will seem very unstable because it's not something that we're familiar with, okay? So, there's a lot of these, there are papers published that outline like the tipping points that we need to worry about in the Earth system. I don't want to go through all of them, but what I want to do is draw a connection between what people have called tipping points and what we've been talking about a lot, right? Which is critical points, right? So our critical points, right, we're thinking about a transition from one state to another state that's associated with some kind of threshold crossing. But our states in particular are phases, right? We can define them as laminar and turbulent. We can define them as fluid-like and solid-like, right? And so what I want to do is outline a few Earth system tipping points that have been talked about quite a bit recently that are related to or can be mapped to critical points that we've talked about in our lectures, right? So one of the ones that I want to, so by the way, in this mapping, I guess, so that's the tipping point, and then, right, just to beat the horse here, right, like, we think about like our critical points, like in this temperature pressure diagram, right? And so is there any relationship between these two things? So one of the ones that I want to think about, that people talk a lot about, is like the catastrophic loss of ice sheets, right? So It's in Antarctica and it's in Greenland. I'll just draw Greenland. So this is Doug's crude drawing of Greenland, right? There's some dimensionality to this, right? So this is an island. It's an island that's covered in ice. It rises up out of the ocean. And essentially, the way that this ice sheet and a lot of ice sheets work is that there are high topography zones in the middle where it snows. That's Doug's snowflakes, right? I don't feel like making them any more details. So, but it snows in the middle, right? And so if you draw this in cross section, right, you have this, you have this situation here where it snows in the middle. This is where you add mass to the glacier, right? When you add mass, you're adding pressure. That causes the glacier to flow, right? And the glacier is going to flow toward the ocean. And when the ice comes and it meets the ocean, this is where the ice melts. And so the steady state situation is that you're raining down snow in the middle, you're adding mass to the middle, you're creating height, which creates a pressure gradient, which drives the ice to creep, right, toward the ocean where it melts. So you're adding mass here, you're flowing here, and you're losing here, right? So if you then think about it in the context of the island, right, you have all of this flow coming from the middle out to the margins, right? So if we think about this, of course, we know that when things get too hot, that ice will melt, and we understand that it can melt faster than it can regenerate by snow. But it turns out that that mass balance, that if we just think about it, that, oh, the glaciers are going to disappear just because it's too hot to have snow. That's not the prominent worry, actually, right? The prominent worry is that the glaciers are going to flow too fast, right? And so how does that happen? So we have to zoom in a little bit on, so let's imagine now that we have the situation of, this is a glacier extending into the ocean. And so the usual scenario is that there's ice. This ice is moving over the bottom. So we'll call this bedrock, and we'll call this like a granular bed, right? And so the scenario is that, the ice is flowing this way, and this is the point where it comes in contact with the ocean. And the glacier thins like this, right? And so now we have the situation where, the ocean is here, the ocean is lapping up against the glacier, right? So what's happening in this scenario is, let me draw this. It's dangerous. I'm going to try and draw a perspective view, right? But so here's the ice front, and there's a few different phenomena that are going on here. Thanks. Not terrible, right? Yeah. Right. So the ice is cracking, right? And when that ice cracks and breaks apart, it makes, see, now I'm running into trouble, right? But, right, we have all these little floating ice cubes here, right? So the ice shelf is breaking apart, cracking, and it's producing this floating suspension of ice cubes in the front, right? Critical phenomena number one. It's been demonstrated that essentially this ice breaks apart, and I don't feel like drawing perspective anymore, but this ice breaks apart, and it makes these icebergs in front in what we call an ice melange. And they are essentially a jammed granular suspension that is floating. And what we know is that the glacier is pushing against this jammed granular front of its own making. And then occasionally it pushes hard enough that it unjams the suspension, or occasionally the suspension just unjams by some other pressure from below. And whether or not it's the unjamming of the suspension by tides or something, or it's the pushing from behind, there's a catastrophic loss of rigidity. And this ice melange will suddenly fluidize and flow. And then it's followed by the glacier breaking apart in the front. So we know that there's this critical phenomena that's happening, that there appears to be this threshold state that the system is drawn to. And it's like whether it's pushed by the glacier or pulled by the suspension, the two are tightly coupled together, right? And so there's a critical phenomenon there, which means that there's a possibility of real sensitivity, right? And this is controlling the mass loss of the glacier in the front. you also have this situation, right? So we have a granular bed that has water running down into it at the base of this glacier, right? And so the glacier can move along very slowly if it's locked on a rock or sediment bed. And then it can get hydraulically lubricated if enough water gets down to the base, and it can lose frictional contact. And it's sort of like an earthquake fault that it can do this again and again, right? So it can exceed a stress state, it can slip a lot and relieve that stress and then get locked up again. And so there's critical phenomena going on there too, right? And so the movement of this glacier and the breaking apart of this glacier at the front are both governed by critical phenomena. And we also have this idea that they're sort of naturally perched at their critical state, right? Under the environment in which they formed, they built up their mass and their slope until, like a sand pile, they were in this condition where they're at the critical point between flowing and not flowing, slipping and not slipping, between falling apart and growing and sliding into the ocean, right? So this is one example of a tipping point that actually, understanding it at its heart, has critical points in it. You buy it? Yeah, you buy it, right? Okay, good. I have a few others, right? Another one that I'm thinking about is, so there's this thing that we worry about, which is that drought causes like what we would call, let's just say, vegetation death, right? So you have areas where it becomes too dry, either natural vegetation or agricultural vegetation. The plants die. The plants die, and the soil is now easier to erode because it's not being held together. And as the soil erodes, it removes the nutrient-rich part of the topsoil that the plants need to get a toehold in, right? And so you basically get like more effective drought conditions. It's not that it makes the drought worse, but that's the erosion is basically stripping away the soil-rich sediment, and it's making the landscape more like a desert environment because you've removed the soil that basically formed in a more temperate condition, right? And so physically, right, so we have this situation, some Bob Ross happy plants. These are happy plants, right? So these happy plants are growing here. And these happy plants are growing. And there's two important things that these plants do. Let's think about first a wind-blown environment, but it could also be, it's also true for underwater, right? But if we're thinking about plants growing in a semi-arid environment, the plants do two important things. So first of all, the roots, of course, literally hold the soil together. So they make the soil harder to erode. They increase the threshold. Right? We talked about the importance of threshold. The other thing they do is they slow the wind down, right? So these plants are an additional drag, and so the turbulent wind is moving across the surface, and when it hits these plants, it slows down. This is why when you go to the beach in New Jersey and they're struggling to keep these sand dunes around so that they can protect the houses, they keep planting plants in neat, tidy rows, and then they keep getting obliterated by the waves, but they keep planting them, because they want the plants to hold the soil together, and they also want the plants to actually encourage sand that's blowing to deposit and lift the landscape up, right? So what happens when we obliterate these nice, happy plants, right? So now we have this part of the surface that I drew in red is under attack. So the effective wind stress has gone up because the drag from the plants is gone. The threshold stress has gone down. You remember that sediment flux transport rules basically look like this. That the flux goes like the fluid stress minus some critical raised to some power that's greater than 1. So we've increased the effective fluid stress by removing the drag. We've decreased the threshold by removing the roots. And so you in this highly nonlinear transport equation, you now have an effective transport rate that is a lot higher, right? And so when the wind blows, right, we now start entraining and picking up sand and dust particles and moving them, right? And when that happens and we strip away the nice organic rich soil that's at the surface, you actually strip it away to material underneath that is even more erodible, that doesn't have all the organic matter that's in it, hasn't been fertilized and with all the plant stuff, right? That's as best I can say it. The other thing is that it's more susceptible to fluid erosion, right? So now we have this situation where often drought is accompanied by higher intensity rain when it does occur, right? So there's less rain overall, but higher intensity rain when it does occur, which means that when the rain comes, it doesn't come often, but when it does, there's more of it than there used to be, which means that we get more overland flow than we used to, which means that, right, we get more fluid-driven erosion, and so particles on the surface are also more susceptible to getting transported away by the overland flow. That also causes this erosion, strips away the soil, has this runaway effect, right? Now, the situation with overland flow is actually a little more pernicious even than the wind one. It's a little more pernicious because there are additional feedbacks. So here we are drawing our badly drawn mountain again, right? And the way to think about this is that imagine that I have a landscape that, for whatever reason, I want to draw one that you can see. Okay. I'm drawing like a contour line here, right? So what I'm trying to show here is that the landscape exists and it initially always has some kind of bumps, right? So if we take my little 1D drawing, but we play it out in a three-dimensional domain, what it means is that, right, we know that water is going to collect into hollows, right? And so when you start to accumulate water in these hollows, they start to erode. And as they erode, they bring in more water. As they bring in more water, there's more stress. They erode, right? And so if you go down slope, what you see is that, right, these topographic contours get exaggerated, right? And what you're forming is what we call rills, erosional channels, right? And so when you introduce fluid, water-driven erosion to a landscape that hasn't had to deal with it before, either because the rainfall intensity went up and now we're getting overland flow where we didn't used to, or because the erosion threshold went down, so now we're getting erosion when we didn't used to for the same amount of rain, that you get this runaway effect. And you need look no further than a construction site or something like that. If you've ever noticed, when they go and they dig up and then they pile a bunch of loose, unvegetated soil over in one steep embankment, and within days and weeks, you can watch these rills develop, and they seem to grow without bound, right? And so when you don't have rills on a steep hill slope, it's because you don't have the conditions for runaway erosion, right? Those kind of landscapes didn't grow up under that kind of condition. When you lower the threshold or you increase the fluid stress, you now introduce this soil and this landscape to a kind of stress that it didn't experience before. We've now actually driven it past a critical point when it wasn't there before. And you have these kind of runaway effects that lead to like catastrophic erosion. Right? So that's another example that has critical points at its heart, right? There's another example that I want to go through. It also involves some happy plants that don't get too attached to because they get destroyed, right? But this is the problem of drought plus human mismanagement of landscapes that leads to wildfire, that then is followed by intense rain, that then, as you could probably anticipate, is followed by debris flows. You know, if you pay attention in the news, you understand that in the last 10 years, at least the coverage of this cycle has expanded greatly, not just in the US, in places like the Southwest, but also now in places like Oregon, also even in places in the mountain west. And part of this is because of increasing droughts and increasing intensity, and part of it is our mismanagement of the landscapes that makes wildfires more intense when they do occur. But from the physical perspective, right, is again, we now have, before a fire, we have some landscape like this with the happy plants that are growing on it, and the happy plants have their happy roots. And what happens after a wildfire is, right, so of course the plants get eliminated, and you burn all of the material down to some depth, right? And so you now have a material that used to be held together by plants and roots. It's no longer held together by plants and roots, right? And so this is a soil where you could say that at the very least the volume fraction of the soil has gone down. It's become looser. There's a lot of holes in the soil that used to be occupied with roots and stuff. But of course you haven't just changed the volume fraction. The roots were mechanically like nets, right? They were actually withstanding tensile stresses and holding the sand together, and you've eliminated that, right? And so, of course, this is changing the threshold and it's changing the hydrology a bunch. And then you rain on it, and what happens is that, this burned soil layer, which is anywhere from a few centimeters to tens of centimeters deep, depending on the fire and the soil and all that stuff, right? But it's still a relatively shallow layer, right? So you have this shallow layer that is burned, is weak, but then underneath of it, you have intact soil where the fire didn't reach that is more densely packed together. There are some other things that make it different, but the main effect is that this burn layer is looser and weaker than the soil underneath. And so when you then get an intense rain, what happens is that the rain gets sucked up rapidly by this very porous, ashy soil, and the rain does not permeate across the boundary between the burned and the unburned soil. So you basically load up this shallow layer with water, you unjam it, and when you unjam it, you create a debris flow, right? When you create the debris flow, you remove any residual living things that might be in the soil that might help it like regenerate more quickly. If you have this catastrophic debris flow, you basically just take it all out, right? So they're very destructive. And you've now created, obviously, a catastrophe, but you also now have a landscape that needs a lot of time to recover. But if you're increasing the pace that fires are coming, and then you're increasing the intensity that rainfall is coming, the soil may not have the chance to regenerate and hold together again. So the threshold has been like irreversibly lowered because it might have some timescale of recovery, but it's getting whacked again before that timescale recovery can occur, right? So we've driven the system from a state that is occasionally debris flowing to one that essentially will debris flow all the time, right? And there are indications that we see this happening in landscapes, and that is more critical phenomena. There are a few others that I was gonna talk about, but I don't wanna go too long because I do wanna get to something hopeful. But I mean, two other critical phenomena that I thought about here. One we talked about yesterday, Ev, but you could even think of corals and coral reef die-off as a critical phenomenon, right? So why do I say that? Well, remember way back early on, I don't think it was lecture 4, we were basically talking about the materials that you see on planet Earth today are the materials that are resilient under that environment, right? And so you see soil, where soil is regenerated at a rate that it is stripped away. And you see ice in a place, not where ice is stable, not melting at all, but where ice is regenerated at the same rate that it is melting, right? Well, you see corals in a place where they can grow. And you see corals in a place where the environment permits them to grow. And so, if we think about, my crude planet Earth, right? Here we are. You get it, right? Those are the continents. But you ask where you find corals, right? And you find corals in this band. It's an equatorial band. You need two things, right? First of all, it's warm. It needs to be really warm in order to precipitate calcium carbonate, which is like the substrate that the microorganisms grow on, right? And so you can only do that in a few warm places on planet Earth, right? And it also needs to be the conditions under which the microbes that colonate this calcium carbonate that precipitates can live, right? And they've literally evolved to live in these environments where calcium carbonate can precipitate, right? So with very few exceptions, there's cold water corals in a few places, but most everywhere that we see corals on planet Earth are in these warm bands where the temperature makes the thermodynamics favorable for calcium carbonate to precipitate. So calcium carbonate is everywhere in the seas. The oceans are super saturated with it. The ocean doesn't want to have as much carbonate as it does, but it turns out there's an energy barrier to get over in order to precipitate it. And so in these warm water environments where the solubility is higher and where the microbes can grow, you meet those conditions. So two things are happening. One is that the rise in temperature is, killing the microbes that essentially help precipitate carbonate and make reefs. And the other is just straight up dissolution, right? So where we're finding this carbonate, where we find reefs is where carbonate is precipitating, it's dissolving too. But it's precipitating and dissolving and precipitating and dissolving. If you raise the temperatures enough, you kill the microbes, but you also switch the balance toward dissolution, right? And so you can't have the microbes that help precipitate it, and you have the temperature conditions that dissolve it more, right? And so in this particular situation, we haven't changed the critical point. It's more like this was a system that evolved to be perched at critical between dissolution and precipitation, but now the environment is changing, and it's changing that balance, right? So that's one example. And what was the other one that I had? Oh, like falling permafrost, but I guess that was for you, John, but I have a nice drawing in here, but it's kind of obvious, right? Basically, in a lot of cold environments, especially in the Arctic, we have soils that are permanently frozen. And the ice that's in the soils is literally a glue that holds the soil together, and that glue is thawing. And so the soil is both losing its glue as the solid ice bridge is turned to liquid, and then the liquid is also either pressurizing and saturating or just lubricating the frictional contacts. And so the threshold is going down because the glue is going away, and the stress state driving the system toward failure is going up. And so what you have is this catastrophic runaway erosion that's happening, where the landscapes that are becoming unglued are just oozing and flowing away very catastrophically, right? So, okay. I want to end on like a little bit of like a happier note, right? So hopefully we have some understanding of the way in which these tipping points or state changes in the Earth system are actually intimately related to the critical phenomena that we've been so interested and concerned about in this course. And, if you're either optimistic or you just want to end on a positive note, then you might want to answer the question, are there any solutions that we can offer, right? Is there anything that learning about the soft Earth can tell us that will help us address some of these concerns about these state changes, right? And I have a few that I want to close on. So one thing that we know is we look at records of the amount of water flowing in rivers, in America anyway, where we have good data, right? So let's just look, say, starting in the 1950s, going to like 1980s, going all the way over here to 2020, right? And if we look at the discharge in rivers, so the amount of water that's been running down them, of course, you have low flows and high flows, sometimes long droughts, things like this, right? And so there's ups and downs of the discharge. But if you look at them over decades, what you see is that this variation in the ups and downs is superimposed on a trend in many rivers. Not all rivers, but in many rivers in America. The trend is a trend of increasing flood magnitudes, right? So here, I should label this, we're drawing the discharge of a river, which remember I call Q, right? And so if you want to call these peaks as like a Q max, the one thing we know is that Q max is going up in hundreds of rivers in America currently, right? So this is the thing, is that immediately when you think increasing peak flows, you think increasing floods for us, right? Makes sense to think about it that way. And indeed, if you think of a river that we have hardened, so that humans have come in and we've hardened the banks. So this could be as extreme as the LA River, where the bed and banks are all cement, or it could be less extreme like what we have here in the Schuylkill in Philly, where like, well, there's a natural bed, but we've got walls and embankments and riprap, that like stuff that we're basically throwing stuff down everywhere to protect the banks, right? So in the situation where a peak, where a Q max goes from here over decades to here, it's clear that more larger peak flows is going to be more flooding, right? So this is what I would call a hard river. All right, and this is the word we use. We harden the river. And when you harden the river, the only response the river can have to an increasing amount of water is to flood. What about a soft river, though, right? So if we think of what is a soft river, it's a river that hasn't been hardened by us, right? And it's also a river that's not bedrock, right? So for us, a soft river is an alluvial river. This is a river that's got sand or pebbles on the bottom. Often the scenario is that it has like mud on the banks. And so what happens to a soft river when the peak floods become larger? We talked about this, right? When the peak floods become larger, remember, we know that this river was adjusted to a state that is just above critical. So if we change the discharge regime, what happens is now we had a situation before where the riverbanks were stable and now the stress is higher. We flipped the riverbanks from being just below critical to just above critical. The riverbanks will erode, right? And the riverbanks will erode, and as they erode, they will take the water and distribute it across, of course. And what's going to happen is that the peak depth is going to go back down. And it's going to go back down to bring the river back to the critical state. So on the one hand, the river being in a critical state means all kinds of things are hard. But on the other hand, soft rivers adjust to climate change. And I didn't just make this up. We now have enough decades of data that are showing that in rivers that are soft and not hardened, that the channel cross sections have been growing in lockstep with increasing discharge. So if you give the river room, it can buffer and accommodate this increasing discharge. And it's only our problem of hardening the river that makes peak discharge mean more flooding. We actually don't need to have more flooding if we just give the river more room to keep itself locked in its near critical state. So I think that that's, a positive development. Another scenario that we think about, we worry about a lot, is sea level rise in coastal environments. And especially, I've spent time thinking about coastal marshes, right? So this isn't a problem that we've talked a lot about in the lecture, right? But let's say here, right, that we have the ocean up against the land. And the situation before humans come along is that we have a big river that comes down. The river, when it approaches the ocean and slows down and deposits sediment, it starts branching, right? And we know that that river, if you think of this as, say, the Mississippi, is also carrying a ton of sediment, right? So the sediment makes these plumes that go off into the ocean. And when the river floods, what happens naturally is that the water spills over its bank, and the gradients here on a river delta like the Mississippi are very small, right? Like, 1 centimeter per kilometer or even 1 millimeter per kilometer, right? Very small elevation changes for distance, very, very small slopes. So when the water spills over bank, it goes everywhere naturally, and it brings that sediment with it, right? And so the deal is that we know that humans are accelerating sea level rise, but we know that even before we accelerated sea level rise, that sea level's been rising for the last 10 to 12,000 years, right? So we take a system that is adjusted to sea level, and then we say that sea level goes up, right? And so when sea level goes up, now this portion of the delta that was above the water, if sea level goes up and it's just passively drowning the delta, this part is now underwater, right? But that's not what happens naturally, right? If the sea level is slow enough, the delta is also bleeding sediment out of its channels during floods, and it can actually deposit sediment to keep rise with that sea level. So up until about 100 years ago, the Mississippi Delta, the Rhine-Meuse Delta, the Amazon Delta, all these deltas around the world were keeping up with 1 to 2 millimeters of sea level rise. And they were just doing it by flooding and spreading out their sediment. Of course, what we've done is come along and armor these rivers, right? So we armor these rivers, and remember I told you if you armor, you're going to flood. But we don't want to flood down here. So we have armored the hell out of them, right? So on the Mississippi River, for example, the levees are extremely high. And anytime that there is the possibility of a flood, we build the levees even higher. And so we now have a situation where the river is a fire hose. It's containing all of its sediment. We don't let any of the sediment bleed over bank. And what happens is the sediment makes it to the ocean. It shoots out in jets. And the sediment gets ejected to the deep ocean. And none of it is there to restore and nourish the marshes. We started doing experimental diversions on the Mississippi. And then we had an accidental diversion during the historic 2011 flood when the Army Corps had to blow up levees and intentionally flood the Delta to save New Orleans. And when we did that, what did we find? We found that one flood could counteract 20 to 30 years of sea level rise, that it deposited enough sediment to counteract 20 to 30 years of sea level rise. So we have this situation. The tipping point here is that when you drown a marsh, it can't come back, right? The marsh has these plants holding together this weird gelatinous porous soil. And when you drown that completely and the plants die, the ecosystem goes away, the soil literally collapses, and you can't get it back, right? But we know that if we can nourish the marshes with enough sediment to keep up with sea level rise, that they won't cross that tipping point. And so we can't do a lot about the marsh we've already lost, but we can do a whole lot about the marsh that we haven't lost yet, right? And then the last little bit that I want to talk about is, we have this situation both with soils that are burning, and they go from being soils that were stable to they get burned and they're unstable. And we also just have a lot of places where soil is generally unstable even without us disturbing it, right? And so we have this idea that simple soils, meaning you could just think of sand, or you could think of a soil that had a lot of organic matter and plants and then it burned, right? In both cases, you've simplified the soil. And we've made the soil that used to have this multi-scale hierarchical stuff, it doesn't have that anymore, right? The thing, if you recall, is that simple soils, if we think about their strength in terms of like a stress-strain curve, right? The simple soils do that, right? So they fail brittly. You load them and they can handle a load, and then they just catastrophically fall apart. That's bad, that's dangerous, right? So one thing that we can think about doing is, what we like to call complexifying soils. So we know that multi-scale interactions and heterogeneous mixtures create soils that are more ductile and that are more resilient to disturbance, right? And we have actually made them in the lab. And one way that we make them in the lab, right, is you can take a sandy soil and you could then add water that's dosed with fine particles, clays or other things like that. And what will happen is that the water will trickle down and the water will find itself inside the it'll make little capillary bridges between the sand, and it concentrates all the fine particles. And what happens is the fine particles get left behind as this precipitate, and they actually hold the big sand grains together. And they make it a lot stronger. Now, we've only studied the physics of this very recently, but it seems like there's this possibility that you could take simple, unstable soils and you could dose them with water and some inert material like fine clays or other things, and you could complexify the soil, right? The idea is that instead we're going to change it from a mechanical response like this to some wide failure envelope that never truly fails, right? Now, we can complexify soils for erosion, but there's another reason to complexify soils, and it's building, right? You like my little house? Looks more like a ghoul, but so right now, there are places on planet Earth where we have been building with soil, and we've been doing it for a long time. We brought this up in the beginning, but the oldest continuously existent buildings on the planet are made of soil. They're made of mud, basically. And you remember when I talked about that, I said, not only are they resilient to a lot of disturbances, but when they crack, you can actually heal them again, right? You can re-wet them, they become soft, and you can heal them. So we know that there are lots of places on Earth where we've been building with earth materials for a long time. It's, in our modern parlance, this is a very sustainable practice because you take material from right there and you build it and make a building right there, and the material has very good physical and thermal properties to it, right? There's a lot of problems of, something like 8 to 10% of our greenhouse gas emissions come from cement. A lot of people are looking for ways to replace cement. Soil seems like a good one. But I talked about this way back in like lecture 4 and 5 that currently there are narrow bands of planet Earth where we seem to be able to build with the soil that's right there, right? It's this Goldilocks thing where like it has to be a wet enough environment that some clays get precipitated, but not so wet that it gets washed away, right? Something like that. So the soils need to be sticky, but not too sticky. The environment needs to be a little wet, but not too wet. And so that has restrained for a long time building with soil or geomaterials to narrow regions. But maybe we can take soils that are on the bubble, on the margin, that currently are not suitable, either because of their composition or because of the environment that they're in. But by complexifying the soil and changing its mechanical properties, we can move the soil into the buildable regime, right? And so potentially by harnessing our understanding of how increasing soil complexity increases or changes mechanical behaviors and increases resilience, we can use this as a way to increase the habitable region of building with soils, if you will. That seems like a good place to stop. So, thanks.